Hello, everybody. Oh, what was that? Oh, right. It always trips me up that I have to turn off all of the places that YouTube wants me to preview what I'm doing before I can actually do anything useful. So, let's talk about. So, I've been gone for about 2 weeks now, week and a half. I was off on vacation last week and had absolutely no internet for the entire week. That's not quite true. I had a little bit of internet one of the days. And I have to say, it was kind of great. Instead of paying attention to my phone or checking Twitter all the time, I was nice and relaxing and reading, and it was great. So, what that means, though, is that we have quite a bit to talk about now. We last weekend, or yes, the not the most recent last weekend, but the weekend before that was BCTF run by, and we can pull it up here. BCTF, which was run by Blue Lotus, I believe. I'll be able to pull this up in a second here and verify that. There was BCTF run by Blue Lotus, which I did a little bit on. I was able to spend maybe 6 hours on it. I think I solved one challenge. That's about it. It was good. I enjoyed the challenge that I worked on, although I didn't have enough time to do a ton of stuff with it, so I didn't do all that much. And then last weekend, that is yesterday and the day before, there was Plaid CTF. And Plaid CTF is one of my favorite CTFs every year. It's run by PPP out of CMU. Well, I guess technically out of CMU is kind of the important part. A lot of the members are alumni from there. And they're people that I personally have been playing against for quite a while, so it's always great to see them putting on good competitions. And unfortunately, my trip home yesterday was delayed by about 3 hours, so I completely missed getting to play any of Plaid CTF at all. So, unfortunately, I can't actually talk about any of the challenges to any real depth as far as during the competition goes. Looks like they had a lot of really good challenges, though. I've heard a lot of good things from people who were able to play, that a lot of them were really difficult. They were great. Like, there's a number of really good, what look like really good pwnables that would have been a ton of fun to play in. Like, pwnable with only 2 solves generally means it's something great in terms of hard difficulty. Although the fact that it wasn't their highest point value one is a little questionable. I assume that there was maybe an unintended solution for Crazy. But yeah, usually they have a ton of great challenges. The one thing I don't notice here is I don't see a quantum challenge or a repeat of the ECE's Revenge. That's kind of been a fixture of Plaid CTF the past few years, so little disappointed I don't see them, although I've never solved either of those, so I can't say much one way or another. So, what are we going to do tonight? So tonight, we're going to take a look at BigPicture a little bit. So BigPicture was one of the pwnables. I know a couple of the people that I play with worked on it, and we're going to take a look at it now and go through it because there's a couple of tricks with it, at least according to them, that are a little bit non-standard as far as most CTFs go. So, we're going to do that. Go through, try and get it solved real quick. Take a look at it. And then afterwards, one thing that I'd really like to take a look at is... what am I doing here? Manticore Trail of Bits. So, Trail of Bits, let's see here. What's the best way to find this thing? Oh, there we go. So, Trail of Bits has been teasing about Manticore now for about a month. And Manticore is their, is a symbolic execution thing from Trail of Bits. So yeah, and I believe, yeah, just a day ago, over the weekend, they finally released it publicly so that anybody could use it. For the past few weeks, it was possible to get a hold of one of the people at Trail and have them give you access to it. But now it's public and everybody can use it. And personally, it looks like a lot of fun things. The one thing that I saw that is super exciting to me and that makes me want to play with it is... where's their wiki? Oh no, they've actually changed this since I was looking at it this afternoon. But the... No. This is the one that really sold. I would like to take a look at it. And this is a write-up from Ehenenfent about solving a pretty simple reversing challenge. It reads some bytes out of standard in here. This is an output from Binary Ninja that they're showing here of the disassembly of a challenge binary. But it reads in some bytes from standard in, then does a compare, some sort of a comparison against a hard-coded value. And if you pass through all of it, you get a "you got it" flag, and it says "you won, good job." So they go through and they show two different ways to solve this in this write-up from using Manticore. And the first of it is doing basically just instrumented debugging, but entirely symbolically, if I understand how all of this works. Basically, they're saying they want to break in at a certain point, read a register value, concatenate it with some context value, and then when they finish, print out a flag. That on its own, pretty cool. I really like the way that looks, that they're able to do that entirely symbolically. However, the one that's pretty exciting here is, if we go past all of that, they're able to do it entirely symbolically and in one shot basically build up a set of constraints and solve for it all in one shot. And personally, that's something that's really cool. It's something that a number of different people have tried to varying degrees, and it's something that, if it works, it's amazing, and I'd like to use it more myself. So, after we finish up with the big picture stuff, I want to take a look at this and see how it goes. One of the big things here is, if you're familiar with Anger, the claim is that Manticore is similar, but different. It's more, their claim is, if you come from a reverse engineering or exploitation background, you may find Manticore more intuitive. Okay, I mean, that is exactly my background, so hopefully this is a little bit easier for me to use than Anger, because personally I find Anger a little clunky and hard to use, but a lot of that has to do with the fact that I've never sat down and really spent a ton of time learning how to use it. So, looking at the code here of what they did with it, all of this kind of just makes sense to me, so hopefully this is something that will fit pretty well. So, that's the plan for tonight. We're going to take a look at Big Picture and then play with Manticore. There's a couple other things that I would like some feedback from the people who are watching. So I posted about this on Twitter this afternoon, that a number of people, looks like actually the majority of people who watch these videos aren't watching them live. They're watching them at some point in the future. I can't get a good grasp on exactly what that is, because of the analytics that YouTube gives you are kind of, they're not very granular. I get kind of a big thing. But I can see that I have some number of people who are watching live, and then it looks like probably over half of the minutes watched are after live. So with the number of people who are watching it after the fact, I'm really curious, how are you watching it, and is there things that I can do to make that easier for you? One of the things that was suggested was to basically, after the fact, have individual, either individual videos, so have a chunk where, so for example, tonight we're going to look at Big Picture. So solving it manually, have that as an individual video is just doing that, and cut out all this discussion about CTFs and stuff from earlier, because if all you care about is watching that, then just watch that. And have, the talk about the CTF and all that as a separate video, and have looking at Manticore as a separate video. Or just have a whole bunch of bookmarks into the video, because you can set it up so that each video, or different points in time, that people can just click on that link and get to just the stuff they want, but you still have the full context. In either case, the plan is to keep the full video available, but if one of those two is going to be more useful for how you personally like to watch these videos, let me know on Twitter. I am /Mermis CTF. And yeah, just send me a message here. Hopefully reply to this one right here. Let me know what you think, because since I'm putting the work into making these, I'd prefer for them to be as useful to the people who are watching them as possible. So give me a second here. I am going to pin this real quick. That way it's a little bit easier to find. So I want to pin that. Yes, replace it. The other thing here is that apparently the fairly resounding response is to finish the PDF crack exploit. So on Wednesdays, we've been looking at trying to find real bugs in real software rather than just looking for CTF bugs. So for the past 2 weeks, we've been looking at a piece of software called PDF Crack, which is a relatively old PDF cracker. It's for breaking the protected, encrypted PDFs. It basically just brute forces them. And we spent the first week getting AFL set up, running through it, taking a quick look at some of the outputs from it. Then the second week was triaging the results from AFL, and then trying to come up with a somewhat realistic exploit for actually landing a vulnerability in this piece of software. And unfortunately, I was hoping that in those 2 weeks we'd be able to finish all of it, but I wasn't able to. So I put up a post here and I asked for some input. Would people like to see that getting finished, or to move on to something else? And it sounds like on Wednesday we will be finishing that up. So if you've enjoyed the PDF crack videos, hopefully this Wednesday will be another one just like it. And while I'm talking about things coming up later in the week, as I would assume a relatively large number of the viewers know, this weekend is the Defcon CTF qualifier. I know for a lot of people, this is probably one of the most important online CTFs of the year, because they're going to be handing out a handful of qualification slots to Defcon finals in July, I believe, this year, which for a lot of people, this is the event every year to do. So it's this weekend. I'm going to spend all weekend bashing my head against things. Hopefully it's super good. It has been for the past several years. Well, all the years I've played in it, it's been pretty good. Although I still hold a little bit of a grudge over getting tricked into watching the Asses of the Caribbean for 6 straight hours, trying to figure out where they hit a flag in that. But that's a completely different story altogether. So make sure that if you're interested, play in this event. Should be a ton of fun. So let's see here. With all of that taken care of, let's go take a look at this binary. So I am going into this more or less blind. I know that it's a pwnable. I have a little bit of an idea from people talking about it, about what it is, what the bug is. Like, I know kind of that it's some heap exploitation stuff, that there's some sort of a write to an index based that they can do. And I know roughly the trick that somebody used to actually solve it. So, other than that, I don't know much. So let's take a look at it real quick. So like I said, let's see here. So we have this. One thing that's interesting is that they gave you the source code for it. I had a number of people mention that. So take a look at. That's not what I wanted at all. Take a look at the source code here. So just taking a look at the. Oh. Before I forget, let's also use screen so that I can actually, look at it usefully. So taking a look at this real quick. So we have the main function, set an alarm. Let's draw a picture. How big? We get a width and a height. They then calloc the width and height. So calloc. Oh, that's the wrong key combination. That one. So calloc is going to give you width times height bytes. Basically what it's doing is it's designed for, I have a data structure of some size, and I have this many elements of that. So we have this right here. This is the calloc here. The first argument is the number of members, and the second argument is the size of each of those members. I don't actually know how much the order of these matter. You just need to know that it's multiplication of the two. It gets used a lot when you're trying to dynamically allocate an array of some data structure, where like the number of them will be variable, but the size of each of them is constant. So that's what it is. The other thing that's important is that calloc will memset it to 0. All the bytes get set to 0 in the pointer that's returned. malloc does not do that. And what that means is if they're only using calloc, things like a use after free don't really do anything. They've already, they might not do anything, depending on exactly how they're set up. Like I can't take advantage of certain types of heap bugs because whenever anything malloc returns has been completely zeroed out and there's no values there. So yeah. So going back to this thing. So we calloc a buffer here for us. It is width times height bytes. Right here. There we go. It is width times height bytes. If they get no buffer back, they give us an error. We then do a char c. While 1, they will fputs to standard out, some sort of a header for us. They then scanf, read some more bytes in for x, y, and c, whatever c is. And then they will plot x, y, c. Okay. If this fails, they break. They scanf for quit. Quit will then call draw. They then free it and return 0. Okay. Where is get? So before we go too far here, let's do ctags dot. So what that's doing is that's generating the tags file so that I can do things like do I have to reload it? Oh no, I'm being silly, aren't I? Ah! Yeah, I'm being silly. I have to do ctags -r if I'm just giving it a single file. Yeah, that looks much bigger. That's what I wanted. Yeah. So basically what ctags, setting ctags up is if you have source code like this, I can use some hotkeys in Vim to jump around in it and know what exactly is going on. So I can say, oh, what's draw? Oh, look, it just jumped me over to where draw is. It's not as useful given that there's, only a screen full of actual text here. But if we're looking at something bigger, like if you're looking at a real project, having something like ctag set up is incredibly useful. Just to be able to jump around, figure out what the function that's getting called is actually doing. So let's read through this real quick. So plot. So plot is checking to make sure that x and y are both less than the width and the height. So we can go from 0 to width. Is that true? So x here is an int, So presumably these are signed ints, so we can give it a negative value here, and that would also fit this. We then get a pointer. And I will say here, for anybody watching this and is a little bit frustrated, if you already solved this, I am cheating a little bit here. I know from some outside information that there's some sort of negative indexing here. So when I see this, I'm kind of guessing already that I'm looking at negative indexing. So no bashing your head that I said, oh, look, these can be negative. So anyway, so we get a pointer here that is going to get x and y. And that's just going to return buff. Buff is this variable up here that was called, which is x times height and y plus y. Okay, so that should let us index negatively outside of our buffer. Then what do? We then printf overwriting this if it is not, if pointer is non-zero. No, if the value at it is non-zero. So it's going to dereference pointer, and if what pointer points at is 0, we will write to it. Otherwise, we will printf we are overwriting it. Okay? Then what? So that's what plot does. It will let us write a pointer into it. Okay? Well, it will let us write a byte at a time into it. Although, if there is something there, it will tell us what it is. Right? That's what I'm seeing here. If there's already a value there, it will print out what it is. Otherwise, it will write to it. And just to make sure here, yeah. Because they don't have braces here, so it's a little tricky, but they will not write if the value is set up. So we do get a read here that we can use a little bit. After we've done as much, so we can do as much plotting as we want, then we can draw. If we draw, what's going to happen? So if we draw, we're going to get more options for that, aren't we? So it's going to keep getting. So for y is, no, we're not going to get an option here. So it's going to do c is this. It will, if c is 0, it will print out a null byte. It will then put char c, where c is the value it got out. Okay, so this will just print out what this image thing looks like. After that, it's going to call what is by, and then we're going to free buff. Okay, that makes sense for the most part. So let's give it a try real quick. So if we come over here, we want to, let's run it in GDB. Take a run of it. How big? We want, and let's make sure we get the formatting here correctly. 1 by 1. Okay. 0, 0. I'm not sure how much the spacing here matters. I can never remember exactly how scanf handles white space, but and then a character, and I'm just going to give it capital A. That's fine. Okay, so we did not give it quit here, so it is printing out what our image looked like and then said bye. Okay, let's break on free. Let's try this again. 2 by 2. Now I can plot 0, 0, A, 1, 0, B, 0, 0, Q. Oh, yeah, that makes sense. 0, 1, Q. Yeah. Okay, so now we're getting into free. So we got Q is at 0, 1. Oh, so they're indexing the opposite of how I expected this to be indexed. So this is 0, 1, this is 1, 1, this is 0, 0, and this is 1, 0. So the bottom left corner is the 0, 0 point. But, okay, so we got that. So what do things look like? Well, first off, let's take a look at what the protections are. I do this every week. I can never quite remember how that's going to get set up. So the first thing here that's going to be tricky is that pi is enabled. So what does that tell us? So pi is going to be enabled, which means if we actually run this, so we have this pgrep BigPicture cat rock 24025 maps. So this is the one that's actually running outside of GDB. So these maps are the ones which are these maps are ASLR'd. The ones in GDB that are these are not ASLR'd, as you can tell by the fact that that address does not look right at all, does it? But take a look at this real quick. So in these maps, we definitely have the binary at an ASLR address. It has its data sections there. We then have some stuff here. So I'm not actually sure where our heap is, which is unfortunate. Well, we can do this the easy way, can't we? Sudo gdb BigPicture. What's my password? That's my password, right? Yeah, that's my password. I want to attach to 24025. Yep. So do they have symbols? They do have symbols. So buff is at this address. So this is the pointer that was returned by calloc. If we take a look at this, let's do 20x. Is this the pointer that was returned by? I'm not sure I believe that anymore. Let's take a look at this. So we are in Plaid CTF, BigPicture. Let's take a look at main. So we have all of it. We have main. So we called calloc. That's buff. And buff is at 2020 there. That is not at 2020. So we want this. The heap will show up after I do the calloc. Oh, yes. That is me being completely dumb there. So I haven't made the first allocation there, so of course there's no heap. Well, what kind of crazy talk is that? So thank you to NASA rejects. So I want to attach now to 24076, and if I do this again, that looks like a little bit more of what I was expecting. So now we have this right here, which is our heap. This is 64-bit. We have things here. They mount a buffer. There's stuff there. Yay! Although that isn't aligned quite. Oh, yes, it is aligned the way. So if we take a look at this, this is the base of the heap. We have a single allocation which has 20 hex bytes allocated to it. So 1, 2 for the metadata, plus the 16 bytes that is the minimum for our 2x2 picture. So if we wrote into it, we would see it there. So the first thing that we notice is that we can't do much here, right? We're not contiguous with anything useful. And taking a look at the, where are we? Taking a look at this, we can only write to negative offsets. And even if we could write to anything else, what's that really going to do? So the first thing that we need is we need some sort of a pointer leak, don't we? Let's think about this for a second. Is there anywhere that could give us a pointer leak reasonably? So we called calloc, which gave us some memory. If we... So what I would expect is that if we did -1, 0, right? No. So if we did x is the first value we give it, and x is multiplied times height, and so I don't want to use that because that's going to be confusing. So if I do 0, -1, I should see that we are trying to overwrite 21 hex, right? That's what I would expect to see. So let's rerun this. We want a 1 by 1. I want 0, -1, a. That worked. Not expect that to work. 0, -1, a. -1, 0. Why did that not tell me? So what I expect to see there... Oh, because of endianness, right? If instead I do this, yeah, I want not that, I want 0, -8, a. Yeah, see, exclamation point is 21 hex, right? Let's verify that real quick. Yeah, it's an exclamation point. So that is giving us the metadata back. Does that do us anything useful? So we're able to read out a byte at a time from negative indexes, but we're in the heap, and the heap is not going to be necessarily aligned with anything. That's unfortunate. Taking a look at this a little bit more, we have so we call calloc with the size we gave it. We then plot it. Yes, I know we hit our alarm. It might be worth patching that out. It's not quite annoying enough yet, but we'll see. So we have the scanf here that will then plot for us. Each time we plot, we calculate it, and we do that. Does this tell us anything? If we are out of bounds? I don't think that tells us anything useful, because we know what the width and height are, because we told it what the width and the height are. Although the width and height are globals, which might be interesting. So we come in here. So we have several things that are set up in the globals in the BSS. But I don't think any of these are going to be immediately useful. So we don't trying to think about this for a minute. So we don't know where this is, though. Because we are pi, we have no idea where our BSS is. We also don't know where our heap is. So that doesn't help us either. So what are we going to do here? So we can't do anything else. We can't get a pointer out of this, right? Because if we could arrange for a malloc and a free prior to that, we'd be fine, but we can't. Is there a trick with a draw? So when we plot, we can get a leak out. When free is only called once here, right? Yeah, free is only called once. Alloc is only called once. So unless we were able to like restart this somehow, and if we could do that, we were already in code execution, so that doesn't get us much. So at locations where we know where they are, there's no useful metadata. At least not in the straightforward scan through here. There is the draw, which if we don't quit, it will draw. When it draws, it spits out a bunch of information to us, and I don't think we care about that. So what? And then it will eventually free it. So rather than going into too much detail here, I'm going to cheat a little bit more, and we're going to talk about how this actually works. So the trick here, if you have already read a write-up on this, I believe there is one already posted on CTF Time. And the basic version is that there are four important sizes when it comes to heap allocations. So this is the write-up that's already out there. And Arbiter, I guess, talks about what exactly is going on here, at least the way that they solved it. And the short version is that they take advantage of one of those sizes. So let's take a look at what's actually going on here. So if we go to OWOBOC for the malloc source code, so this should have, and let's close this, that my computer's a little bit less unhappy. Do they have, yeah, so we have calloc in here. What does calloc actually do? So calloc has, you know, just some stuff. We check some sizes, checks to see if the hook is set up, then we're going to call it. All those tooltips. We then check it, we verify it, and basically, eventually we'll fall down and we will call int malloc. And so when it comes to int malloc, so int malloc is the internal malloc. It's how malloc actually does its stuff. There's a wrapper around it, which is the libc malloc, which has things like if you want to set up a malloc or a free hook and things like that. But int malloc is what actually does all the hard work and manages all these allocations. So what are the important sizes? Well, the first important size is the fast bin size. So by default, that is going to be 80 hex bytes. And so any allocations that are smaller than 80 hex bytes are going to be serviced by the fast bins if there's a free bin there. The next important size is the normal bins, or small bins. And if we take a look at this real quick, we have is in small bin range. So we have the n bins, we then have, tooltips, go away. Where are we? So we have the small bin index, and this is just macroed out here. Off my head, I'm not quite sure what this value is. I believe it's 400 hex bytes. So number of small bins times the width. What does that look like? So 64 times malloc alignment is 16 bytes. So Python hex 64 times 16 is 400 hex bytes. Yep. So the small bins are anything between 80 hex bytes and 400 hex bytes. And just like the fast bins, those are just going to be serviced from the small bins range if there is room in the small bins. Then, if you are a large request, and I don't think they have a fancy name for this, do they? They are the large bins. So we have the fast bins, we have the small bins, and we have the large bins. Basically, if it's a large request, we're going to call basically the malloc consolidate if there are fast chunks. Basically what that's doing is if there's anything in the fast bins, we're going to consolidate everything in the heap and turn it into a more contiguous region. We're not going to move anything, but the important part here is that the fast bins on their own don't consolidate. So if I have, and I'm going to pull this up real quick. We're going to use real paint this time so people can actually read it. So if we have a bin here and we have a bin here, and these are both, 10 hex bytes in size, and we free both of them, what's going to be in the fast bins are 2 10 hex byte bins, not one 20 hex byte bin. Well, actually it'd be 30 hex bytes because we get the header back because they're contiguous. Instead, we just get 2 10 hex byte bins. So, yeah. What this consolidate does, though, is that's actually going to go through, it's going to dump everything out of the fast bins, and if it can, it will combine them together and have a nice, useful piece of memory instead. So, we did that, and we ended up going through all that. And then what? After that, we have other stuff here. And there's a fair amount here. And the short version is that there's a ton of stuff here that can be done. But the part that's important, at least for what we're doing, is that if all of this fails, and so basically if none of the stuff can service it, let me make sure that's right. This is a lot of code. But yeah. So they process the recently freed or remembered chunks. The output loop is here because we might not realize until near the end of malloc that we should have consolidated, so we must do so and retry. Okay, so we go through, we try and consolidate everything else. We keep trying to consolidate stuff, blah, 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 blah. So we're consolidating out all these small bins, I believe. If it is a large request, scan through the chunks of the current bin in sorted order to find a size that fits. Blah, 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 blah. So we search for it again. None of these are able to service us. Finally we get down here. So if it's large enough, split off the chunk bordering the end of memory held in AV top. Note that this is in accord with the best fit search rule. So if out of all the other stuff we did, we couldn't service it any other way, we're going to take a chunk off the top of the heap and we're going to use that. Awesome. So we do that. We will potentially do that. However, so if the size is greater than or equal to NB, which I don't remember what NB is, because of course it's something they use constantly. It's the number of bytes. So if the size of if the size of the chunk at the top of the heap, so the amount of space left at the end, is greater than or equal to the number of bytes we need plus the minimum size for a header, then we can service it. If it isn't, so we failed here, we don't have any fast bins left, the very last thing it's going to do is it's going to call sysmalloc. And sysmalloc goes through a ton of code, but the important part for us here is that it will use mmap. What does that mean for us? Well, that doesn't mean anything immediately useful, except that, and let's get this real quick. So let's run this real quick. So first off, let's talk about what we need to do here. So we have this right here. We want this x/20x that. So we want buff. GX, of course. So this is the buffer that was returned to us. I'm typing terribly here, aren't I? The important thing is that we need to ask for more memory than this right here. So we need to ask for more than 20FE1 bytes in memory. So because we're giving it decimal values, OX20FE1, so we need to ask for at least that many bytes. I can do that. So I want to restart this. Yes, I want 1 by 135,138 bytes in size. Oh, no. Oops. 1 by 135,138 bytes in size. Awesome. And if we dump the same thing here, we have, oh, look, what is this? So this pointer looks completely different than the ones we were getting before. Why is that? Because when we take a look at it, it looks basically like a heap chunk, doesn't it? Like we have a size. That size is this thing plus the metadata size. So what is this? And the answer is, this is the chunk that malloc return, or mmap returned. So under the hood, malloc is going to service this request using mmap, which is going to just ask the kernel, give me some memory. Here's a size I need. You can put it wherever you want. Now, the part that's important here is that this chunk of memory is going to be square. That is not quite square in the middle of where I thought it would be. It's going to put it up against other stuff. And the reason why that's important is that it's going to be near things that we actually care about, things that we could overwrite and do something useful with. What's interesting here is that running this in GDB didn't align it quite the way that I was expecting it to. Which one do we want here? So we have this one. Continue, sure. Continue, sure. We want to run it again. 1 by 135,138 bytes. It's X. 135,138. Yes. pgrep BigPic. Oh. Attach 24311. So now, what do we want? So we take a look at these. We have this nice big chunk of memory that's been allocated for us. We have up here, if we dump this, we have the actual bytes that were returned. So this right here is what was returned for buff. So we can see it looks fine, right? It looks pretty normal. And we still don't get anything. But, and what's important here is if we look at how this was aligned. So when mmap returns a pointer, it's going to try and return things that are at least somewhat contiguous. And the reason why that's important is because the way paging works internally in the kernel. So for each chunk of memory that it has to keep track of, because this is all virtual memory, like this is not backed directly by a RAM chip. This is virtual memory that could be anywhere on that chunk of RAM. It needs to keep a record for it. So each one that it has takes overhead, and that's very important because they want to keep their overhead low. So mmap is going to return things that are near to each other. In particular, it's going to return things that are right next to each other most of the time. And basically, what's important for us is that because of how this gets laid out, we actually line up reasonably well. We have this right here, and we can say, this is the pointer that we had. We want to, yeah, let's just kill it. Bang, pgrep, big picture, going to attach again. Oh no, we forgot to allocate anything. 35138. So what do we see here? We have, this is the buffer that was returned. And I know, the reason I know this is because the size here, this is the amount of memory we asked for, which was a little over 20,000 hex bytes. I believe it was 21,000, which was rounded up to a 4K page. And that's just for alignment reasons. So this is the one that we had. And so what we're doing here is I'm saying, oh no, this thing and this thing. Turns out the offset from the pointer that was returned by mmap to libc is static. And the reason for that is because all of these up here were all returned by mmap. So internally in LD is going to, so LD is the loader. I don't remember what exactly it stands for. But LD is how Linux is going to load a process into memory. And the important part for this right here is that when we use LD, it's going to use mmap to put things into memory for the SOs. So even though these are all ASLR, like I don't know what this pointer is because I don't have a good way to get that out. What I do know is the relative offset, because I know what the relative offset for all of these are. So all of this memory, so all the libc stuff, all the LD stuff, and anything else that we try and return with mmap, it's all going to be at the same basic offset. While I say that, there might be a caveat there in that the fact that this is sliding into a region of memory, like the specific size we gave it looks like it's sliding into an existing chunk of memory. And I'm not quite sure why it's doing that. So it's possible that if we gave it a slightly bigger size, we'd end up someplace else. But the short version is that when we use mmap, it's going to be at a consistent offset from the other stuff that was returned from mmap, which includes all the stuff in libc. So what does that tell us? Well, it tells us that we can do free hook. Here's the free hook. And I want this thing right here minus this thing right here. So, oh, I'm sorry. That was in the wrong order, wasn't it? I want this minus this. Oh, and of course it doesn't give me a... So if I index at that offset, what it's going to do is it's actually going to write into the free hook, right? That's the way that should work. And this should work not just in the one that is non-ASLR'd, should work in the one that's ASLR'd, or in the one that is ASLR'd. It should be the same offset in the ASLR'd one, or non-ASLR'd one too. So let's do this again. 1 by 135, 138. I then want to write to 0, comma, negative 1976408A. Why is that there? Am I off by... I'm off by 10 hex bytes. I want... because... yeah. That is the value I want. Negative 1976424A. That's not what exactly I expect either, is it? 0, negative 1976425A. Okay. I've broken something terribly, and I'm not quite sure why. We pulled in a value there that looks completely wrong. Okay, so let's start here. iproc mappings. So this is the thing that we returned. This looks fine. We want this minus 1976424. There are zeros there. Is my math wrong? Well, yes. My math is wrong. Huh. So it's possible this is not quite as static as I thought it. Oh, right. Because we're running in GDB. GDB has made some allocations here, hasn't it? GDB has changed the way that things allocated. Is that true? Maybe that's not true. Looking at these, those look the same. If I do this minus this, that is a different value. Interesting. I was not expecting that. If I run it again. So 1 by 135138. And I want to write to 0, negative 1960024, A, 0, comma, negative 1960023, A, 0, comma, negative 1960022, A, negative 1960021, A, 0, 1960021, A, out. 960020, A. Let's do one more. 1960019, A. And now I want to do some stuff. I have a breakpoint in malloc still. No, I have a breakpoint in free, which is fine. And if I do x/gx and free hook, oh no, did I mess up? Oh, I did mess up, but I'm close. So basically, I needed to be 16 hex bytes earlier, and it should work. So what I expect to see here is that if I come in here, I want to write a exploit.py from pwn import star s is equal to process BigPicture s dot, let's just read it all in. We know we want to s.sendLine 1 by 135138. So remember, this was just big enough that we can't service it with the amount of memory that's currently there. We then went to s.sendLine 0, comma, and we should be able to use this value over here on the right, which I believe is negative 1976424. And we want to write an A into it. And what we should be, actually, what's the best way to do this? %d negative 1976424 plus I? That's what I want. For I in x range 8 bytes. We want to do that. s.interactive. So if this works the way that I certainly hope it works, I should be able to do this right here. I got a SigSeg V. I like SigSeg Vs. Let's kill this. I want to do GDB a BigPicture core. Oh no, we're dying in a plot. Why are we dying in a plot? We're dying in a plot because we're trying to write to that thing. And if we do... We did not overwrite that at all. That is unfortunate. So, what do we have here? We have our mappings, and we have... We do not have the pointer that was returned by mmap. Because it's a core dump, they did not save that off. So if we print out this, we can see that this is what buff was. So print this minus this. I don't see A's. Oh, I totally used the wrong value, didn't I? This is the value from... This is not the right value at all. That's why that didn't work. 0040. Okay. Save that. Kill this. Let's do Python or RM core Python exploit. Oh, we got closer, didn't we? We got closer, but we're still not getting what we want. So plus 1960040. Minus 3. So this is pretty clearly... So why are we failing? We are trying to read from racks. Why did we fail here? We tried to write to racks. Racks is probably... So racks is 87AB, which is 7F6002D. So am I just off by a little bit? So I'm off by 4,000 bytes, 4,000 hex bytes. Otherwise, I'm basically exactly where I want to be. So this again. By? That's not what I expected at all. Oh, we did get a Jeep. We did get a core dump. Yeah, that's what I expected to see. So what we have here is we wrote A's into the free hook, which is what we wanted to do. Although, is that what we wanted to do? So again, let's think about this for a second. So we have we can write into the free hook and make it call A's. But that's not going to do anything useful, is it? Because we don't know any of the pointers to tell it where it should call instead. Because ideally what we're going to do here is we're going to point the free hook at system. Hello, CFI. Ideally what we're going to do is we're going to point the free hook at system so that we can then write /binsh into the buffer. Because to free our buffer, it's going to call system for us, system binsh. But we don't have any pointers right now. So how are we going to solve this? Well, there's a couple ways we can solve this. The easiest way, I think, is we can use that plot thing, right? So when we call plot, if there's a non-zero value where we're trying to write to, it will tell us what was there instead of just using it. So what do? So the easiest way, I think, is we can use the got in Libc to tell us where Libc is. we dump this out. No. Was I wrong? Did I grab the wrong one? Should be one of these, shouldn't it? Yeah, there we go. Well, what is this? Like, I'm not entirely sure what these are. Yeah, that's a thing. What's this? Nope. So what I'm hoping for here is, so these are pointers in memory. So these are pointers that are going to be at a static offset from our buffer that we should be able to then print out to us. And hopefully, one of these has a nice, convenient name. Like minimal line. No, that's a pointer into the PLT for it. Oh, that's where the PLT is, though, right? No. Let me think about this for a second. Those have not been used yet, which is why that's like that. So these have not been used. This one might have been used. It has, but we don't have a symbol for it. How about this one? I want something with a name that I can remember. Oh, no. Give me a convenient name. That's not a convenient name. Oh, and I used the same one twice. I mean, that's C-Alec. Why has that not been resolved? It's a little weird. Okay. So what other ways can we resolve this? So the basic version here is we want to use one of these pointers. We can get it to return these pointers to us by trying to overwrite them and get a non-zero value from it. So if I say I get back this pointer right here, this is GIDL find DSO for object. This is one of the pointers that Libc has to know it needs it for some reason. Okay. So I want to print this minus the base of Libc, which is this. And this, again, is a static offset. So what we can do here is we can say the GI offset is 4053536. And we can say that the offset to get to it is this. No, I'm sorry. Oh no. We want the one that is 20. So EA20, which is this. So we want this right here is print this. So we have this value. But what I really want is I have this. I don't want to print that. I want to print this. No. Print this minus this minus that. So negative 1986496. And so what I expect to see here is 4i in x range 8. s.sendLine. Well, first let's clean this again. s.clean. We want 0%d a. And we want to do get offset plus I. And let's do s.interactive again here. So what I expect to see here, let's go to 4. Yeah, this looks fine. We run this. 04 assemble we don't know. Okay. Run it again. Ends in 7F. That looks plausible, right? One thing to keep in mind is we just completely screwed the program from exiting properly because we just overwrote those 2 high bytes with A's. So this program will never work right. But if we go into 3, bang, pgrep big, we attach 2487. Yes, go ahead and kill it. So if we do iproc mappings, I expect to see that x/20gx from here, we have this pointer right here. We just completely bashed. Fortunately, we bashed too many bytes here because we're off by 8 bytes for some reason. Oh, because we started from this one, went backwards. So we need to actually add 8 bytes to it. So we get this pointer instead. We want to be in here. Let's just add it over here. Plus 8. So what do we get here? So we send line. We then want to do, let's do this the easy way, right? We have buff is equal to nothing. S dot read until overwriting space. S dot read line 1. So we want to take just the first byte off of this thing. Actually, you know what? We can do it that way too. We don't have to do slicing. Plus equals. We're just going to print repr buff. What do we get? Oh, right, because it's actually going to succeed. Duh. Replace 6 here. If we do this again, look at that. That looks a whole lot like a real pointer, doesn't it? And if we do a uprint hex u64 buff plus 00 times 2. Because remember, the top 2 bytes are null bytes, which we can't print out. So if we do this, oh, what? Oh, I should put those inside, shouldn't I? We have what looks a lot like a pointer. And if we do libc base is equal to this minus gi offset, we should be able to do print hex libc base. Oh, I should type better. Libc base. I should see that, again, looks a whole lot like the libc we want to have. So, what else do we want to do? We want to say that the libc base is not just some, well, actually, let's check that real quick. So pgrep BigPicture. We want to attach this 24647. Yes, we want to do an x/s. So we should see an elf here. We do see an elf header. And if we do iproc mappings, we see that this is in fact the start of our libc. Awesome. That's exactly what we wanted to see here. I'm trying to remember how to do this properly. So we're not going to bother to do this remotely. So there is a way in pwnTools. I can never remember what it is. It's just s.libc? It is just s.libc. So libc is equal to s.libc. And what's happening is because we're using a local process, pwnTools can just say what libc you're using and find it out. Like it pulls it out for me. So I don't have to go search on my system and find out what it is. I can just say, give me the one that this process is currently using. I have libc.base is equal to libc base. And then I want to do, so system is equal to libc.symbols system. But we want to pack that. So we want to do that, and instead of A, we want to have it be system I. Is this what we want? I'm not sure this is what we want. This might end up reversing endianness. Endianness. A times 8. Okay, so we got a sig V, which is kind of what we expect. GDB BigPicture core. Yeah, that did what we wanted. Okay. Oh, right. I forgot the most important part here. For I in X range len bench. And let's actually look this up. There's a way to do this from phone tools, and I can never remember what it is. I want this thing. So, there is, I don't remember where it is. So there is in the something will turn what bin sh is. There we go. I want the sh string. So if I do, is it just sh string? From pwn import star sh string. What? Routines here are for getting any null terminated sequence of bytes evaluated intact by any shell. Oh, this doesn't do what I thought it did at all. Never mind. That's unfortunate. Yeah. So we want to do s.sendLine 0, comma, I, comma, %c. %d. Percent I, bench I. So what this should do, let's just do this all the way. And so what this is doing is this is triggering that quit condition. If we actually wrote quit out, I believe it would give us basically what we want. Leg. And look, a shell. Oh. Well, that worked. It did not quite do exactly what I expected it to do. Yeah, we have a shell now. Who am I? Look at me. So that's how we did this. It's a little bit messy. So just to go over again what we did here. We did, we're going to do, we start the process. We're sending this size. And what the size is this something big enough to trigger mmap to have to service our calloc request. And what this is 1 byte larger than the default size for the arena that malloc is going to use to service requests. Then, because it's going to use mmap, because internally it's going to use mmap, we know that any buffer that is returned by mmap, assuming sizes stay consistent run to run, are going to be at a consistent offset from each other. That includes things like the different libraries. So one thing that's important that comes up in CTFs occasionally, I can think of it coming up at least a couple of times in the past year, is that libc and ld are going to be at a consistent slide from each other. So if we get a pointer to either one, we can get a pointer to both of them. And so the challenge that I'm thinking of in particular where this mattered was we got a, actually, now that I think about it, I think it was from Defcon Quals last year, was you got a pointer to the Libc, you got a pointer to Libc, and you had to do ROP. But you needed a gadget out of LD to make it all work. And so you needed to know that the fact that those are going to be at the same offset from each other every single run. You don't have to try and break ASLR to get that. They're just always going to be the same offset from each other. What we're doing here is we're taking advantage of exactly that fact. We give malloc a size which is large enough that it's going to have to use mmap under the hood to service it. So now we know that buffer is going to be a consistent offset away from all the stuff in Libc that we want to have. What we do here is then we have the GI offset, which this is, I found a pointer in the Libc got, I believe that's what that was. I don't actually know what it is, I just kind of poked around until I found something that was a pointer. And basically this is the offset to get to this symbol, and then what the pointer returns is this many bytes into Libc. So we use this right here to dump out a pointer into Libc. We then calculate out what Libc base is. We get the Libc for the current process. We then use that to muck with it a little bit. We then just get system now, and we're going to replace the free hook with system. This right here is getting this is the offset to the free hook from our buffer. We're just going to write the pointer into system into that. And then we're going to call binsh. Basically, we write binsh into our buffer. And we then send this to bail out of the program. It frees our buffer, which then calls binsh for us. And that's it. Relatively straightforward. And that's how we solved it. So, that is big picture. So, now that we've done this, we can take this right here is the URL, vim readme.md. This is the video for tonight. We want to git add exploit.py and git add the readme here. And what all do I have to commit? I have some stuff to commit here. So BigPicture exploit. And what's my status here? Whoa, that's a lot of stuff. Let's wait to push until after this so I can actually verify things. So that's that. I will push that a little bit later with how this exploit actually worked. So now to the part that I am super excited to actually take a look at, which is Manticore. So I have done absolutely nothing with Manticore yet, so I am about as blind as anybody else here is. I know that it is a symbolic execution tool. I know that Trail of Bits wrote it, and I have at least a reasonable grasp on how symbolic execution actually works, especially when it comes to using Z3. So let us just... Whoa, I don't know what these things do. What's worse, it happens. Oh, I hate those shortcuts are different. So what I just did there was I did Control-Shift-C to copy out of Firefox, because the terminal I'm using, Control-Shift-C will copy from, and Control-Shift-V will paste into. Problem is that in Firefox it's a different hotkey altogether, and it does completely different things, so bleh. Oh, and we didn't even copy it. So we want to sudo apt-get install some stuff. That's an interesting error. But metadata was ignored due to errors. I have a feeling this install is very unhappy right now, and I will probably be getting rid of it soon. Let's actually clear out all of these real quick. We already finished that. Q exit. Exit. So, where were we? So we ran that right there. We're going to run this right here. We are already up to date. We then want to cd tools. This is the directory where I keep various tools that I might want. We're going to run this thing right here. We are now installing Capstone with no binary. I don't know what it is, but apparently there's something special about it. So hopefully this does something cool. So we want to cd into examples, right? Cd Linux make. So Manticore basic. So the basics of how this works, at least my understanding, is that when we run Manticore basic, it is going to use Manticore to do exploration of standard in. So, I knew I should have moved over there. Linux, cd mcore. What all do we have here? Cat test 001.standard in. Okay. 2. So that symbol and a space did something different than at A. Oh, and we're supposed to pipe these into. Okay. Cat mcore test 1 standard in piped into basic. It is greater than 41. It is less than or equal to 41. Interesting. So what on earth did we just do? So this is the program. It's going to read. It will read up to 4 bytes into command. If command is greater than 41, it will print it out. Otherwise, it'll be less than, and it'll print that out. Makes sense? And what else did they tell us? So when we ran, this is the, no. So executor info. So we set up a loading program basic, workspace, mcore, generating test case number 1 for state number 3. Program finished correctly, program finished correctly. Okay. It looks like it basically just tried stuff and it worked. I'll buy that that's a thing. Cat stir and compare. Sorry, terminal, I did not mean to kill you. Okay, so minimal toy example with input output. So we have buffer, we'll read 100 hex bytes into buffer. We then compare it with a zara zara, and we will then printf zara zara if it's there, otherwise not found. So if we do manticore stir and compare. So I suspect what's going to happen here is that this is going to take a long time because it is trying to solve. Or not. Well, now I'm just entirely confused. I was expecting this to take much longer. So we're generating test cases. Okay. cd mcore for this thing. Star.standard in. Huh. Cat test 001.standard in. So that just sent a whole bunch of Z's. And then it sent whatever that is. That, so the first thing it did was it sent a whole bunch of Z's. That. Oh, I'm guessing that. Hmm. I assume that what it's doing is it's internally figuring out that we can get what we're looking to get. So what we're seeing here is we're slowly building up what this string actually looks like. So it took 8 test cases. And if we do find in mcore, which one was this? mcore 4 dash name slash star dot standard in dash dash exec dot cat that piped to dot slash stir and compare. This work? Oh, it's only 1 dash. What? That is not true at all. There we go. Nope. My cat not found. Okay. Why can I not do this? This is doing what I expect. You know what? Let's just do this the other way. Test 001 dot standard in piped to dot slash stir and compare. Not found. 2 not found. 7 8 Zara. So if we actually just cat this, so this succeeds. Interesting. So what we did here, right, is we went through and we did symbolic solving to get to all of the different paths in this program, trying to figure out what exactly is going on. That's really interesting that it's that easy to do that I can just give it some stuff and it just kind of figures stuff out. What about, so CTF, events, Plaid, BigPicture. So if I just do Manticore, BigPicture. I'm really curious what happens here, right? So if I understand the way Manticore works, because I didn't do anything at all, I just said, here's a binary, go. It's going to try and see from standard in all the different paths in the program I can get to, and it's going to try and solve for them. What I expect here is that we are now a non-trivial program. We went from a very simple, we look at some stuff, to try and solve for everything. Like, this should come up with a ton of stuff. I kind of expect this to kind of choke and not be able to do much, but I'm not sure. So the part that I'm super excited about trying out is, oh, that scanf is going to kill it, isn't it? It's not going to have the slightest clue what to do inside of scanf. So one of the things, if you're not familiar about them, about how the symbolic execution stuff works, is they typically, the way that they work is they're going to try and create a unique input which gets you to someplace in the program. The way that, from my very brief understanding, Manticore does it is they're going to, like, I can give it a script here, and I can, oh, that's the wrong scripts. I want the ones in the example scripts. Examples, script. I want something like, sure, let's take a look at that. So this right here is basically saying they have a binary. In this case, there's some specific address you pass in is the second argument. We set up a hook, which is basically you tell Manticore to, at this point in memory, run this function. So we introduce sim, which is introducing symbolic value to this offset. The val is a new symbolic value of size 32. I assume that's 32 bits. We set up taint of taint ID. Taint ID is some tag we can give it. So we're basically setting up taint that is 32 bits in size and we can do stuff with. We then want to write an integer into memory, which is val and 32 bits. Okay, so we've basically, if I understand this correctly, we have said that here is something we care about. We want to write 32 bits into whatever this magic address is. There's then a has tainted operands function that's been defined here. For operand and operands, which is something, we're going to read that operand. If is symbolic and taint ID in the taint for that operand, we return true, otherwise false. We then hook. We can either hook every instruction or not. So we're going to hook on none to check taint. We then pull out an individual instruction. If it is a compare or a test, we check to see if there are tainted operands. If so, we print it out, which is what we got here. Basically what this is done is this is basically just done pretty simply. We said at this address, whatever this gross shell stuff does, we want to say that there's some symbolic value that we care about. There's some stack variable, because that's what we're doing here, right? Is we're saying that RBP minus CX, for whatever reason, we can control it. We're going to say that is the address we care about. So we're going to give it taint. We say that this is a symbolic value, and then we're going to write it into memory that way. And I am entirely talking about my ass right here, but my assumption is that the reason we do that is because by writing it in like this, as we follow on, we will know where it's used if it's tainted. So we did the introduce here to taint it. We then, on every instruction from here on out, for every instruction, we're going to check to see if it's a compare or a test. If it is, and one of the instructions is tainted, then we're going to print out the address of the instruction we're at. We're going to print out the mnemonic for it, and we're going to print out the op stir. So basically, we're going to just print out what each of those are, and in theory, we should be able to say that each of these is a EAX, and each of these we can control. Go verify. So what is this thing? So we were up here. Tools. I want Manticore. Examples. Linux. Where is this thing? Oh, this was introduce symbolic, right? Where is it? Examples. Script. Oh, no, that's not what I wanted at all. Oh. So I actually do have to run this thing. Okay, I can run this thing. Oh, hey, look at that. Unimplemented syscall. So apparently we got as far as the first test case where we hit a syscall that we can't do anything with and it died. That's unfortunate. How is this thing implemented? So I'm assuming the alarm stuff is what choked on it. That's unfortunate. But where were we? We come back over here. cd source, cd script, cd source. That's what we want to run. So we now have a state explorer binary. So source/state explorer.c. What is this thing actually doing? So we have our main here. If argc is less than 2, we're going to fill from standard in value. And then we do this stuff. Ew. Basically, what this thing over here is doing, so this is the script that they put together. And basically what they're doing here is they want to print out what are all the comparisons we can actually control in some way or other. So we check to see if value and OXFF is 0. If it is, we don't have one branch. Otherwise, we're going to check the next higher byte. Otherwise, we're going to go and check the next higher byte. Basically, we're checking to see if that low byte is 0, which is, I assume, this first one. Then we check to see if it's greater than 40 hex, which would print out this this comparison is the next place that the tainted data was used. Then there's another one, which I assume is down here. Yeah, it's probably this one right here. And then there should be a test to see if it's above 1,000 hex to print out this side or this side. We then check to see that there's another test. Now we're going back over here. We check to see all of these to print out other stuff. And then we can finally dump out this stuff. Again, the program itself is pretty simple here. It doesn't actually do anything super interesting. What's interesting is that using Manticore, they were able to write the script, which introduces taint of some variable. They've tainted it, and now they want to know all the things we can do with that. So if you think about what you could do with something like this, is you could set up and say, at this function, I control this argument. What does this what would this argument get me if I can control it? Now things like this are rarely useful for pwnables. It's relatively uncommon that you need to do solving of any sort for a pwnable. What it does come up with a lot is RE challenges. There are plenty of RE challenges over the years that you were able to, if you knew how to use it properly, just point anger at it and blah, here's a flag. It just spits it out. Hopefully, Manticore can do something similar. And at least to me, this looks a lot easier to understand than anger stuff does. Like looking at the anger stuff and getting all the environment set up and plugging all the pieces in and understanding all of their stuff, while it's a great thing and I'm really glad they open sourced it and let people use it, personally, I find it confusing and hard to understand, so I don't really use it. Whereas this looks like something that I could get my hand around and be able to use on a more regular basis. So right now, I don't have any solid examples of doing that, but hopefully over the next couple months of playing CTF, there will be challenges that come up where I can actually use something like Manticore to do something useful, and I'll be able to talk about it more in the future. So I think it's about all that I have right now. We went through BigPicture, we solved it, we landed a local exploit. We could have done a remote one, but I don't find that quite as interesting. We already have it working on one machine. I can go through the trouble of plugging all the different pieces in and using their Libc and throwing it at them. But because we're not getting flags anymore, I don't know how useful that is to show. So we did that. We landed BigPicture, and we looked at Manticore a little bit, and I poked around at it and tried to see what I could do with it. Other than that, I don't really have much to do for tonight, so I think I'm probably going to call it a night a little bit early. Things to keep in mind, if you've stuck with me this far. Defcon Quals is this weekend. You should totally play. It's probably going to have a ton of very hard challenges across probably a lot of pwnables, a lot of RE challenges, but they usually do a pretty good job of including a whole bunch of non-RE and pwnable challenges too. But I would expect plenty of hard challenges, lots of fun things to look at, hopefully really hard things to look at and bash your head against all weekend. And then next week, hopefully that'll mean I'll have plenty of fun stuff to talk about and say, wow, this was a really cool idea, or wow, that was a terrible idea. Why did they do it that way? We'll see. Other than that, Wednesday, we'll be going back to PDF Crack one more time, hopefully one more time, to actually land an exploit against it. And hopefully by the end of the day on Wednesday, we will have a working exploit against PDF Crack, our real-world bug that we had to cheat a little bit to make work. And after that, we'll be looking at Python for our future 0-day Wednesdays. I think it's about everything. The one thing that I do request is that if you are one of the people who watches my videos after the fact, you don't watch them live, please give me some feedback on Twitter about how you'd like to be able to watch them. I know that a big 2-hour video like this is pretty hard to sit through. Like, you know, if you are watching it straight through, that is amazing and you are awesome. But that might not be the best way for a lot of people to consume these videos and understand them. If you'd rather have them split up or tagged or things like that, send me a message on Twitter, let me know. I'd like to hear from people who are actually watching these, so that I know what is most useful to you, because me, I get most of my value out of just sitting here and doing them. Like, the value here for me was I got to land another pwnable and take a look at Manticore, and while I did it, some people got some entertainment and hopefully some education out of it too. So whatever I can do to make it more entertaining and educational for you, I will try and do. So let me know. And if you have any other questions or comments, feel free to reach out to me. Thanks, everybody. Bye.